concept of force is at the core of mechanics, because the interaction between force and the bodies manifests itself through the motion of bodies, and there are certain laws which govern this interaction. In the context of Newtonian mechanics, there certain laws have been enunciated over the period of let us say about 450 years, and these laws we will go through quickly now. First is the Stevenius law for combination of forces. Well, suppose there is a force F1 in direction as shown here, and there is a second force F2 . Now, how do these two forces combine? We have seen that the combination is through the parallelogram law of forces or triangular law of forces. So, I am just indicating the parallelogram law of forces, that is the force F1 and F2, they form the two adjacent sides of a parallelogram, and the diagonal of the parallelogram gives us the resultant force. This law assigns the vector property to the forces. If we move to the next law, the laws of Newton's. So, first I will discuss the first law due to Newton. Every particle continues in a state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. That is, if we do not apply any force and the particle or the body is at rest, it will continue to be in rest. If the body or the particle is moving in a straight line with a uniform velocity, it will continue to do so if we do not apply any forces. But as soon as we apply the forces, this state of rest or uniform motion will change. That is the first law due to Newton. The second law of motion due to Newton is the change of motion is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. Well, what it says that as soon as we apply the force, the earlier state of rest or motion will change, and this change will be proportional to the magnitude as well as the direction of the force. If the magnitude of the force is higher, the change will be higher, and similarly if the magnitude is lower, the change will be small. Secondly, the direction in which this change takes place is governed by the direction of the force. Now, if we look at these two laws of motion carefully, these concepts of motion and rest, they need to be looked into in a great detail. Well, there are two or three concepts or notions associated with this. First is the how to define the state of rest or relative motion. Well, it is a common experience that if you are traveling in a train, then if you look from the window of the train, the trees etc. or other things, they appear to be in motion opposite to the motion of the train. If the train is moving forward, the trees and other things on the ground, they will be appearing to be moving in the opposite direction. Well, to an observer or to a person who is standing on ground, of course, the tree and other things are at rest. So, it means the concept of rest or uniform motion is related to the person, or it is a relative concept. relative to the observer. For most of the analysis or problems encountered in Newtonian mechanics, it is good enough to take Earth as the body which is at absolute rest. But if you look at some of the problems involving motion of missiles or other bodies like sometimes cyclones, etc., then we have to invoke our knowledge that Earth is not at rest, it is rotating about its own axis, and also it is orbiting about Sun. So, for such problems, the fixed observer cannot be taken as one standing on Earth. It has to be taken maybe an observer on Sun. For motion of galaxies and other heavenly bodies, maybe that is not sufficient. You may have to fix an observer very far outside the galaxies. So, depending upon the nature of the problem, the fixed reference or fixed observer is to be chosen very carefully. Since we will be mostly dealing with engineering problems, that is structures or motion of bodies on Earth, so we will be considering a frame of reference which is fixed relative to the Earth. Now, suppose there are two frames of reference, one is fixed to the Earth and the other is moving at a uniform velocity relative to the first observer, uniform velocity in a straight line. Then again we cannot distinguish between the two observers, because even if a body is observed in a frame which is under uniform motion, the forces will not be required for this motion, because the forces are proportional to the acceleration, change in motion. That is, a body moving at, or an observer moving at a uniform velocity has zero acceleration. So, it means that all those bodies in which are moving relative to each other at uniform velocity in a straight line, they will be treated at par, and the set of all such observers is called the inertial set. Okay. So, when the third concept involved is the relativistic concept. Naturally, when the speeds of bodies under analysis is very high as compared to comparable to the speed of light, then I have already made a statement that classical or Newtonian mechanics is not adequate. We have to resort to relativistic mechanics due to Einstein. So, for our course, for our analysis, it is sufficient to consider Newtonian mechanics, and for the prerequisite for the Newtonian mechanics is that we fix an observer to the ground, to our earth, and then all set of observers or reference frames which are in relative motion with respect to each other through a uniform velocity along a straight line, they are at par. Such a set is the inertial set. The third law of Newton states that to every action there is an equal and opposite reaction. Now, this law, whereas the first two laws they were concerned with the motion of a particle or a rigid body, here in the third law we are discussing the interaction between the bodies themselves. So, whenever there are two bodies or more bodies which are in contact with each other and they interact with each other, then the action of, let us say, body number 1 on 2 is equal and opposite to the action of body number 2 on 1. The fourth important law of classical mechanics or Newtonian mechanics is the law of gravitation. This is the interaction, whereas the third law was the interaction between the particles or bodies in contact. This is the interaction between the bodies which are separated from each other by some distance. So, this is the law of interaction for at a distance. What does it say? Two particles are attracted towards each other along the line connecting them with a force whose magnitude is directly proportional to the product of masses of the bodies, of course, and inversely proportional to the square of the distance between the particles. Let us look at this law more carefully. That is, the two bodies have an interaction of the kind of attraction towards each other, and this interaction or force of interaction is along a direction. So, law states both the direction and magnitude is along a line connecting the two particles. So, you connect the center points of these two particles and then join them. So, that defines the direction of interaction or direction of the attractive force, and the magnitude is proportional to the product of the two of the masses. Please do not confuse mass with the volume or the weight. It is the amount of matter, as we have clarified in lecture 1. So, it is proportional to the product of the masses and inversely proportional to the square of the distance between these two particles. So, when this law is stated analytically, it says that the magnitude of the force of interaction F is proportional to m1 into m2 divided by r square. R is the distance between the two particles, and if the proportionality is replaced by the equality sign through introducing a constant of proportionality g, which is called the universal constant, then the law states that the magnitude of the force is g times m1 into m2 over r square. Okay. So, this is the Newton's gravitational law. Well, this is illustrated graphically here. Suppose m1 and m2 are the two particles or bodies, and the center of these two particles are located in the Cartesian coordinates, so that the position vector of the center of m1 is r1 and the position vector of the center of m2 is r2. They are illustrated here. So, the line connected the mass m1 to m2, the straight line, is illustrated as the vector r12. Then r12 vector is equal to position vector of 2 minus position vector of 1, and this can be written as the distance, the scalar distance r into the unit vector along this line of connection, okay, E. So, unit vector is E. So, force on particle m1 due to m2 is given as, it is the attractive force in the direction of E. So, g into m1 m2 over r square into the unit vector along the connecting line, and conversely the force on m2 due to m1 is negative of the earlier force. So, minus g m1 m2 over r square into E. So, that the vector is now in the opposite direction. So, after having discussed the basic laws of mechanics and understood the role of force, now let us see if how we can analyze various types of forces, maybe replace them with simpler forces or some other quantities of mechanics. So, first we will consider equivalent force system. A force system consists of two types of quantities. One is called forces as such, and the other is called moments, or well, we will, for the time being, we will have a pair of forces with equivalent with opposite directions, but separated from each other by some distance, and they are called coupled. So, but the couple itself manifests through a moment. So, force has two types of actions. One is the push and the other is pull. So, push, it pushes a body or a particle, or it pulls a body. So, and the second type of action of a force is the turning action produced about a point arbitrary in space, maybe designated as point O. So, that is the second type of influence or action of the force. Now, two systems of forces, systems means forces consisting of individual forces or couples. Two systems of forces are equivalent if their actions are same, that is, they have the same push and pull effect as well as the turning effect. Now, I will give you the few examples of equivalent system of forces. First is, suppose there is a single force F whose line of action is AB as shown here, and I want to shift it to a new location. Earlier location is maybe any point over here, and now I want to shift it to a new point. What I will do is that at point O I will have two equal and opposite forces. One is the force equal in magnitude and same in direction at point O. So, I will call this as force F, and an opposite force, same magnitude, same line of action, but sense is opposite. So, it is minus F. Okay. So, one is F, the other is minus F. So, I have not changed the given problem. Now, what I will do is that I will take F force here and minus F force here, and I will call it as a couple. So, a combination of two forces F and minus F, one passing through the given point, you may call it as O dash, and the second force is passing through a new point O, which is pre-designated. So, this constitutes a couple. So, the earlier system of a single force is equivalent to a parallel force, same in magnitude and direction, but shifted to a new position O, and a couple of two forces F and minus F, and the moment of this couple, you remember we have already discussed the moment of a couple, which is equal to R cross F, where R is the position vector from point O to any point on the line of action. So, suppose I take this as R, vector R. Okay. So, the equivalent force system is a force F and a couple of moments C given by R cross F, where R is an arbitrary vector starting from O to a point on the line of action of the force F as given. Okay. Second example of equivalent force system, suppose we are given a, let us say, n number of forces F1, F2 and so on up to Fn, okay, and we want to shift all these forces, n number of forces, to a new location O. What I will do is that, using the previous example, I will shift the force F1 to a new position, and in doing so I will be creating a couple which the moment of that couple is R1 crossed with F1. Okay. Similarly, F2 can be shifted to a new location and a couple is created, R2 vector crossed with F2 vector, and so on so forth up to the Fn nth force shifted to the new location, and the additional couple will be Rn vector crossed with Fn force. Okay. So, if I add up all these vectors, forces with forces and moments with moments, then the sum of all these forces passing through the single point O is Fi summation I going from 1 to n. This is the vector addition, and the sum of all the moments of the couples, well, we have again discussed it earlier that couples are free vectors. So, as long as we know the point about which we have to consider the forces, then it is a material. So, this, when I add up all these couples, moments of couples, this will be Ri crossed with Fi, I going from 1 to n. So, the given system of forces is equivalent to a single resultant force Fr, and a plus is a single moment Cr, which is the summation of all the individual moments. So, what we have learnt is that if we are given any system of forces, we can replace them by a single resultant force plus a single moment which represents the moments of the couples involved in shifting the forces to a given point. Let us fix up our ideas with the help of an example which states that there are two forces, force F1 which is 10 I unit vector plus 3 j unit vector plus 6 k unit vector, plus F2 6 I 3 j minus 2 k newtons, and a couple moment, additional couple moment is given, which consists of two equal and opposite forces of 10 newtons as shown here, separated by a distance of 3 meters, so that you can easily see that the moment will be equal to 3 into 10 30 I in the by right hand screw system in the negative x direction. Okay. The forces are shown. Find the resultant force system located at the origin. That is, we want to shift all the forces to the origin, and in doing so, what is the resultant force and what is the resultant moment? That is our objective. Well, the resultant force, since there are only two forces, the force of 10 newtons are equal and opposite, so they will cancel, their sum will be 0. So, the other two forces are F1 and F2, which are added vectorially to give us 10 I plus 3 j plus 6 k plus 6 I plus 3 j minus 2 k. So, the resultant force is 16I plus 6J plus 4K newtons. That is simple. Now, the moment due to the shifting of forces to the origin can be easily obtained. The moment of the force F1 is R1 crossed with F1. If I go back to the figure, this is F1, and since any point on the line of action of the force is good enough, so R1 is the vector joining O with the, this is R1. Similarly, R2 can be obtained by joining O with 10, 3, 0 point. So, the cross product is taken R1 crossed with F1, R2 similarly for the next moment of the force F2, R2 crossed with F2. So, the cross product, we have already seen how to calculate the cross product. You can do it as the determinant of the matrix. So, I will not go through the details of this calculation because you can do it. So, the second moment is minus 6I plus 20J plus 12K Newton meters, and the moment due to the couple, that is a free vector as we have illustrated earlier, is minus 30I. So, it can be supposed to be acting about any point in space. Hence, the resultant moment of M1, M2 and the couple moment is addition of these three vectors, and the resultant comes out to be minus 15I minus 10J minus 8K Newton meters. Okay. So, the equivalent force system to the given force system is the resultant force of 16I plus 6J plus 4K newtons and a moment of minus 15I 10J minus 10J minus 8K. Now, the question is this equivalent force system consisting of the resultant force and the resultant moment, can we further simplify this? Is there a way that these two things can be merged to get only one simple vector quantity? Well, the answer is it is possible sometimes. What are those special cases? Well, if the resultant force itself comes out to be 0, then you are left with only the resultant moment and nothing can be, it cannot be further simplified. That is the only quantity. Okay. Or if the resultant moment is 0, then the equivalent system consists of a single force Fr. But there is a situation when both Fr and Mr are non-zero, but still we can further simplify it, namely the case when Mr and Fr are mutually perpendicular vector quantities. That is, their dot product is 0. Okay. In that case, we can further shift the force Fr to a new position, and the new position is to be selected in such a way that the quantity Mr is equal to the distance between the vector distance between the old position and the new position crossed with Fr. Okay. So, to show that, we will make this statement that the simplest force system, that is consisting of a single force, is obtained if all forces and couples lie in a plane. Okay. Because when the couples lie in a plane, lie in a plane, then the moment of that couple is perpendicular to the plane and hence is normal to the given forces. So, our condition is fulfilled, a single force can be obtained which is equivalent to the given system. And second case is when all forces are parallel to each other. Then in shifting these forces to a single point, the moments will be created which are perpendicular to the forces, okay, to the direction of the forces. Again our condition is satisfied. Let us illustrate this with the help of examples here. First is the example of a beam which is subjected to a force of 75 Newton at a distance of 2.5 meters from the left hand end, and second force is of a horizontal force of 100 newtons which is acting on a bracket fixed to the beam. Let us say this is the bracket which is welded to the beam at these joints, and then on the tip of the bracket we have a horizontal pull of 100 newtons, and the distance between the tip of the bracket and the center of the beam is 0.5 meters, okay, and all other distances are given. Now let us see how we can replace this system consisting of a couple of moment 50 Newton meter, a vertical force downward 75 newtons, and a horizontal force towards right 100 newtons. Well, the resultant force very easy to see, 100 newtons, which is the horizontal force in the x direction, and downward y direction 75 Newton force, so minus 75 J. And the moment of these forces when they are shifted to the origin, going back to the figure, origin O, so the x, y, z coordinates are also illustrated here. So we will have, we can easily see that the downward force minus 75 J, it's missed out, this is vector J unit vector, so crossed with 2.5 K, it's I, sorry for the mistakes, this is I unit vector, okay, and this is oh yeah, well, the moment of this force, when I shift this force to this point, so it will be creating a moment along the z axis, okay, in the inward direction. So you can see that when I shift this force, one force downward here and one force upward, so the moment of the couple will be the clockwise moment, which will be in the minus z direction. So let us see. It will be force 75 into distance 2.5 in the minus and the other moment will be 100 into 2.5, again that will be in the clockwise direction, so minus K, and this is the 50 K is the moment of the couple already given. Yeah. See, once again let us look over the moments of see, when I shift 75 newtons, I will take it two equivalent opposite forces, one force in this direction, one force in this direction. So this vertically upward force and downward force, they constitute a couple whose moment will be in a clockwise moment. So, that will be in the minus k direction. Similarly, this force of 100 newtons to the right is shifted to point O along this line of action. So, in doing so, we will again generate a moment which is clockwise, again in the minus k direction. So, this is the first moment, this is the second moment, and this is the given couple moment of 50 k in the plus in the anti-clockwise direction. So, the net moment is 187.5 in the minus k direction, that is clockwise along the z axis, and the forces are having components in the x and y direction. So, the resultant force lies in the xy plane. So, it is obvious that the moment vector mr and the force vector fr, they are mutually perpendicular to each other. Hence, we can further simplify this system of forces and replace this system by a single force Fr passing through a new point, let us say point P. Okay. So, how we can get this? We have as shown, the resultant moment minus 187.5 is equal to ROP crossed with the resultant force Fr. So, that will be equal to, let us say the distance is from the origin to the new point of action of the force, resultant force is x bar. So, 75 into the distance, that is x bar. So, in shifting it, we will create again a anti-clockwise clockwise moment. So, it will be minus 75 x bar in the minus z direction, that is minus k bar k hat. So, solving this, 187.5 divided by 75, which is equal to 2.5 meter. So, this x bar comes out to be 2.5 meters. So, the original force system is replaced by a simpler force system passing through P, whose distance is given over here. Let us take up an example of parallel forces. A system of vertical forces is given. There is a downward force passing at point A of 20 newtons, upward force parallel to z axis again of 30 newtons passing at point B, similarly at C 40 newton downward force. The locations of A and B, A, B, C are given, and in addition there is a moment is indicated by two arrows of magnitude 20 I plus 20 J Newton meters lying in the xy plane. Okay. So, replace this system by the simplest resultant. Where does this resultant intersect the xy plane? Let us see this. If I, because all the forces are parallel to z axis, so they are in the parallel to the k unit vector. So, the first force, second, third force all in the k direction. So, the resultant is very easily obtained, minus 30 k newtons, and in shifting these parallel forces to the origin, we have r cross f. You can again see that the point A is, the location of point A is 0.4 I plus 0.2 J. So, the position vector of A is joining this point with this point. Similarly, position vector of B is joining this origin to this point B, and for C. So, these are the given position vectors crossed with their respective forces, and this last term represents the moment in the xy plane, 20I plus 20j. So, if after carrying out this cross multiplication, you add up all these vectors, so you will get minus 18I plus 38j Newton meters. Force is in the k direction, moment in the xy plane, because it has components in the x and y direction. So, it means the force is perpendicular to the moment, resultant moment. Hence, it is possible to replace it by a simpler force system, namely Mr. Let us say that this simpler force system is passing through a point x bar comma y bar. Okay. Then, as stated, Mr must be equal to ROP crossed with Fr. So, xi plus yj crossed with the resultant force minus 30 k equal to the resultant moment Mr, which is minus 18I plus 38j. So, carrying out this cross multiplication and simplifying, we have this vector equation 30 x bar j minus 30 y bar I equal to minus 18I plus 38j. This vector equation is equivalent to two scalar ones, and solving these two equations we get x bar is equal to 1.2667 meters, y bar is equal to 0.6 meters, and hence we have replaced the given force system with a simpler one, which consists of a single force parallel to the z axis, but now passing through this new point x bar y bar. The application of this parallel force system is very useful, namely in the calculation or in the determination of the center of gravity as well as center of pressure. Let us see. Suppose there is a body an arbitrary of arbitrary shape and size, and we consider a small element of this body, which the element is dV. Phi is the mass density of the material. So, each infinitesimal element is being pulled towards the center of earth. This is the gravitational pull and governed by Newton's law of gravitation. So, suppose we have this coordinate system x, y, z, z is the vertical direction. So, the force of gravity will be in the minus z direction. So, an infinitesimal element of the body of volume dV will have a force acting on it parallel to z axis in the negative direction as phi dV, because mass density into the volume will give me the mass of this infinitesimal element times g, the acceleration due to gravity, and minus k is the direction. So, dV can be written as dx times dy times dz. So, the elementary force on this on this infinitesimal element is minus phi g dx dy dz in the k direction. Okay. And the total gravitational force on this body will be obtained by summing up all these parallel forces on infinitesimal elements, and in the limit it will be replaced by the volume integration. So, the equation 1 gives me the total resultant force on this body, and take the moment of the gravitational forces on each and every infinitesimal element about point O, which is the origin of the coordinate system. So, r crossed with the elementary force. So, when we integrate it, that gives me the resultant moment. Now, we have Mr and Fr. Now, this can be replaced by a single force. Now, how we can do it? again the resultant moment should be equal to the resultant force passing through the point x bar, y bar, z bar. So, it means this will be equal to mr is equal to minus, I am taking out this negative sign from here. So, minus xi plus yj plus zk crossed with this resultant force, and considering this when I substitute mr over here and the right hand side, again we will have a vector equation equivalent to two scalar equations, and from there we will get x bar and y bar, which is given by volume integral phi g x dx dy z dy dz divided by phi g dx dy dz. So, similarly y bar is given by this expression. Now, suppose I turn the body through 90 degree and do the same operation, then I can in a similar manner find z bar, which is phi g z dx dy z dz integrated over the entire volume divided by the magnitude of the resultant force. So, having obtained this x bar y bar z bar, that is, this is the point through which the resultant force is passing, resultant gravitational force is passing. Such a point is called the center of gravity of the given body. On similar lines, we can consider the pressure acting on a plane surface. The concept of center of gravity was for the volume. Now, volume is a three-dimensional manifold. For the surface, which is a two-dimensional manifold, we have similarly the concept of center of pressure. Suppose here it is an inclined surface, it need not be horizontal, let us say it is inclined at certain angle to the horizontal. So, this surface, and in that plane of the surface I have x bar, x dash, y dash as coordinate axis, and in the same manner I consider a very small element of surface dA, which can be written as dx prime, dx dash, dy dash. Now, the unit normal to this surface is the vector n, and the pressure is acting on this surface. So, on this small element of surface, the pressure, which is force per unit area. So, P times dA, that is the area of this small element, and this is acting in the actually this unit vector should be in the, this is the unit vector. So, it is in the negative of the unit vector, the pressure is acting, pressure is compressive pressure. So, it is in the opposite sense as to the outer normal. So, dP is equal to P times dA, that is the magnitude, times the unit vector in the opposite to the outer normal, that is minus n unit vector. The resultant force of pressure is obtained by integrating over the entire area as given over here. So, this is equal to minus P unit vector to the in the outer normal direction dx dash dy dash, and we can shift this parallel system of forces to all these forces are shifted to the origin by considering these moments as usual. And let us define the center of pressure x bar y bar in the as the point through which the resultant pressure acts. So, carrying out the same analysis as for the center of gravity, we see that x bar is equal to xp dx, that is the area integral of the moments divided by the area integral of the pressure force, that is the resultant magnitude of the resultant pressure force, and similarly y bar is given by this expression. Let us consider one simple example where there is a distribution of pressure. Suppose a plate of size 3 meter by 4 meter is given, it is lying on the plane xy and z is normal to it. So, there is a distribution of pressure, a parabolic distribution. So, a rectangular plate of 4 meter by 3 meter is subjected to a load distribution which varies parabolically from 0 to 40 Newton per meter square. So, it increases in a parabolic manner, 0 at this and 40 at the other corner, but it is uniform along the x axis. Along the y axis it is increasing, but it is uniform along the x axis. Replace this pressure distribution by a single force and find the location through which it acts, and this location is called the center of pressure. Okay. Let us see how first of all we will find out the pressure distribution in the proper vectorial manner. Because the force is acting downward parallel to the z axis, so its unit vector is k, okay, and due to parabolic distribution it is proportional to the square root of y, and a is the constant of proportionality which is to be determined from the boundary conditions. Well, we know that when y is equal to 3 meters, the pressure, the magnitude of this force is, this pressure is 40. So, if I substitute y is equal to 3 meters in this equation and simplifying it, I can easily get a is equal to minus 40 divided by root of 3. So, the pressure in a vectorial manner is written as minus 40 divided by root 3 into y under root in the k direction. Okay. And if I integrate it over the entire plate, I get the total pressure force, and this is obtained as minus 320 newtons in the k direction. To find the center of pressure, we will take the moments and do the analysis. Well, because the distribution of the force along x axis is uniform, rectangular distribution, so the x coordinate of the center of pressure will be the mid length of the this rectangle, that is x will be 4 by 2. That always remember, for the rectangular distribution, it is the center of the rectangle. So, it is 4 by 2, that is 2 meters. For y bar, that is y coordinate of the center of pressure, we take the moments about x axis. So, py into dxy, that is divided by, this should be divided by the net force, pressure force. So, carrying through this simple integration, we will have the net force, you remember, is 320, which was found earlier. So, in the denominator we will have 320, and the y coordinate will be obtained as 9 by 5 meters. So, therefore, the center of pressure is 2 meters and 1.8 meters, 2 meters along x axis and 1.8 along y axis. So, I will close today's lecture here. In the next lecture, we will be considering the equilibrium of forces. Thank you very much.